Okay, hi, and welcome back to Unit 5.1. This is part 2. Again, we are still working on quantifying equilibrium. And in part 1, we really just kind of went over equilibrium, what it is, why it's important, etc. In this unit, we're actually going to start, this video, we're going to actually start quantifying. So let's talk about quantifying equilibrium. The way that we quantify equilibrium, assign a number to it, is use what's called the equilibrium constant. And you may recall that to write the equilibrium constant expression, which is given as symbol K, is we take the balanced chemical equation and we put the concentrations of products over the concentrations of reactants. And of course, we raise the concentrations of each product and reactant by its corresponding coefficient. So for example, concentration of product D is raised to the little d since that's the coefficient of product D. And similarly, reactant A is raised, its concentration is raised to the power of little a since that's its coefficient in the balanced chemical equation. So this is pretty much our simple, very simple plug and chug. But here are some things you may not know or may not remember about equilibrium constant that are super important for us to know. First of all, it quantifies the ratios of reactants to products at equilibrium. So a couple of things are important there. It's a ratio of reactants to products and it's at equilibrium. And remember, the products are on top. That's all going to be important when you're sort of comparing things, cases when it's not at equilibrium, etc. All right. Another thing to know that if you have a large K, like a K much greater than 1, that means that the forward reaction is favored. And that should sort of make sense because if you have a large K, so a value that's greater than 1, since this is a fraction, that means that that numerator, where the products are bigger than the denominator where the reactants are. So that means you have a lot of products. The only way you can get to have a lot more products than reactants is if the forward reaction, which synthesizes the products or makes the products, is more favored. On the flip side, if you have a small k, a k much smaller than 1, that means the reverse reaction is favored. And so that means that in that case, the forward reaction is not favored or it's less spontaneous. And again, this is the tie-in to thermo, using that term spontaneous. So in that case, that again should make sense because if the reverse reaction is favored, that means you have more products going to reactants. And so you should have a lot more reactants. And when you have a lot more reactants, that means you have a larger denominator than a numerator. So your value of K should be less than 1. So you're using also fraction skills here when you're dealing with equilibrium constant. And of course, we could utilize these arrows to sort of indicate to you whether the forward reaction or the reverse reaction is favored. This is going back to the part 1 video. Another thing to know about equilibrium setting up an equilibrium constant, one more thing, is that we can only include species that are in their aqueous or gaseous phase. Meaning, for example, if D, which is one of our products in this reaction, is a solid, we could not write it in the equilibrium reaction expression. So in that case, we would just take this out. You basically replace it with 1. So it'll be 1 times e to the power of a little e. Or just don't write it in at all. And the same thing if A, let's say A was a liquid, because we don't include solids or liquids. So if A was a liquid, again, you would just take it out. You would not write it into the equilibrium expression. And that, again, is super important because you could have a heterogeneous reaction system. Okay, so since this is pretty basic, the first CFU is basically just write the equilibrium constant expression. And what do I mean by that? I don't want a number here. I want an expression that looks like this for the reaction shown. Pause the video now, and when you press play again, the answer will be revealed. Okay, so this is what your answer should look like. All of these are in aqueous phase. That means that we can include everything into this equilibrium expression. And remember to raise NH3 to the power of 2 since it has a coefficient of 2. Everything else has a coefficient of 1, so their powers are the invisible one. Cool. All right, so now let's go into our second CFU. We've learned how to write the equilibrium constant expression. Now let's actually start plugging in some numbers into those expressions to calculate it. And for that, we're going to use that chart that was, I think that's slide 7 on your handout packet. We went over that slide at the end of the part 1. So if you want to calculate the equilibrium constant, they're saying for the synthesis of N2O4. So we have to be very careful because once you're dealing with equilibrium, you could be taking the perspective of the forward or the reverse reaction. Since they're meaning the synthesis means to make, we're making N2O4 in the forward reaction. So going from NO2 to making N2O4. So basically, you're going to write the equilibrium expression for the reaction in that as it's written here. And remember the first three experiments, those are the synthesis. And then the last one, it's sort of the reverse reaction. We talked about that in part 1, but it actually doesn't matter. The only thing that matters is that you're using these equilibrium concentrations that are listed here, and you're plugging one for one experiment. You're going to plug that into your value for your K expression. All right, so pause the video now. When you press play again, the answer will be revealed. Okay, so if you did experiment 1, this is what your work should look like. First off, notice that the equilibrium expression, again, is products over reactants. And here I have my products over my reactant. And then if you did it for experiment 1, then you would plug in these numbers appropriately. So this is NO2, so I'd plug that into the bottom. And this one is N2O4, so I'd plug that into the top. And this is the value that I get, 4.7. So that's experiment 1. If you chose to do experiment 2, then again, you would do the same thing. Of course, you're plugging in different numbers. The value is about the same, 4.74. And that's something that should make sense, is that the value should be about the same because the equilibrium constant is a constant at a given temperature. So since all of these reactions are occurring at 100 degrees Celsius, then the K should be the same. Last one, if you're doing experiment 3 or 4, then here you have the values are the same at equilibrium, so you would get the same numbers once you plug them in. Okay, let's try CFU2 now. This one's a little tricky. So in this case, they're asking you to calculate the equilibrium constant for the decomposition of N2O4. That means that when we're speaking of the decomposition of N2O4, we had to flip the way the reaction is written. Because if we're talking about decomposition, your reactant will be the product for the forward, right? So the reactant now is N2O4 and it's decomposing into 2 NO2s. So here's the balanced chemical equation. Again, you're using the information in the tables there. For any experiment that you want, plug it in and then see the value that you get. Great, so first off, our K expression is sort of the reciprocal of what we saw before, since the product now is NO2. And this is our K expression. If you did experiment 1, this is what you should have gotten, 0.211. If you did experiment 2, you also got 0.211. And if you did experiment 3 or 4, you got 0.213. So you'll notice again that they're all the same, and that makes sense because K is a constant at a given temperature. All right. Now that we see how to calculate it, do we always get a nice convenient chart like this? No. So there are cases where we can't determine the equilibrium concentrations, because that's what you need in order to calculate the K, is what the concentrations are at equilibrium, not initially, not halfway through, but at equilibrium. So what if you couldn't determine the equilibrium concentrations of your reactants and products? What do you do then? Well, in this case, you have this handy dandy tool, which is known as Hess's law. That's right, Hess who's back. All right, so again, Hess's law is very useful if you're calculating K when you can't measure the equilibrium concentration, or it's a reaction where you're just trying to predict the value of K. It's not, you haven't tested the reaction yet, you just want to predict it. And you may recall from Hess's law, the way that it works is, let's say you have 2 or more reactions that you can manipulate, like manipulating meaning flip the reaction, or multiplying all of the coefficients by a certain number. Once you manipulate those reactions, and then you can combine them, like meaning just like add them up and cancel out things that are found on both sides of the arrow, like the NOs for here, for example. And when you add that all up, it gets you another reaction. And this will be known as like your overall or final reaction that you're trying to aim for. So whatever you did to the reaction, you would do the same thing to the delta H's or whatever the thermodynamic terms. And then you would add those delta H's. So that's what we did for Hess's law. Something similar is happening here for K, but for K, it's not going to be so simple as just adding. It's going to be a little different. All right, so first off, let's say we have these 2 reactions, 1 and 2, and we have their K expression and a value for K. So K1 is 0.014. For K2, the value is 7.2. And we want to figure out the value of K for reaction 3. Now, we can't determine it experimentally for whatever reason, but we know K1 and we know K2. So the question is, how can we combine these two in order to get them to equal to K3? So what you need to do in this case is actually focus on the Ks, K1, K2, those expressions, and how to get to K3. Since Ks are our equilibrium constants, are ratios, we're really dealing with just multiplying and dividing here. So we're not actually going to add anything up, we're going to multiply or divide things. That's how we combine Ks. And in this case, if you multiply K1 and K2 together, those two expressions, it will give you the expression for K3. So that means that you can do the same thing with their K values. If you can multiply the 0.014 by 7.2, and that will give you the value for K3. So if you want to, maybe you might want to just pause the video right now, just sort of think about what I just said. Okay, so here's your CFU. I want you to prove that we actually multiply K1 and K2 to get to K3, and we're not adding them up. And the way I want you to prove it is simply just multiplying the K's together. So you have your K expressions. You're going to take the expression for K1, which is this one here, and multiply with the expression for K2, and then see if that is equivalent to K3. Pause the video now. When you press play again, the answer will be revealed. Great, so here's the work here. This is the K1 and the K2 expressions. I just multiplied them together. And one thing that you'll notice is that the BR2s, they're gonna cancel out, so I'll just cancel them out right now. And what you're left with in the end is NO2 squared times BrCl2, which is in the numerator here, times NOBr squared times concentration of Cl2, which is in the denominator, and so that matches up with K3. So for Ks, when you're dealing with equilibrium constants, for Hess's law, you're going to multiply, divide things. You're not going to add things up. All right, I want you to try the same thing in this CFU. You're given these two reactions. You're going to determine the K for the last reaction. My hint to you is to actually write out the equilibrium expressions for reactions 1, 2, and 3 and see how they will get you to the equilibrium expression for K3. So see how these would sort of combine to give you K3. Okay, so here is the answer. What you're going to do in this case, you actually have to square the first reaction K1 and then multiply it by K2. And then when you do that with their values, that's going to give you the value for K3. And this is the number that I have for K3. All right, so that's it for part 2. I hope you found this video helpful. Have a quality day.